It's good day. It's my pleasure to moderate this session. We have two interesting talks about application AI for different domains, and two talks. We have 1 hour and 30 minutes for all reporters. And say 20-25 minutes for your presentation. After that, we can discuss and let's go. Okay, welcome. First presentation is ML-based web services for rental price prediction, architecture, and implementation for real estate market. Also, this presentation, Kostya Fedchenko and Vitaliy Kobets. Vitaliy, welcome for your presentation.
Thank you so much. Dear Chair, dear participants of the PhD section of this ICTRI conference, my name is Vitaliy Kobets, and I would like to introduce for you the research ML-based web service for rental price prediction, architecture and implementation for real estate market, prepared by me and my PhD student Kostya Fedchenko from Kherson State University, Ukraine. So you can see structure of our research with motivation, related works, data and methodology, main results, discussion with limitations, and conclusions. So, investors, lenders, and governments are interested in housing price forecasting systems to improve their decisions and activities related to purchasing and lending. Home buyers need an accurate model to evaluate their investment, sellers to evaluate profits, lenders to evaluate risk, and auditors to better manage their assets portfolios. Services based on artificial intelligence and machine learning are attracting more attention than traditional statistical modeling for estimating housing prices. The growing interest is driven by the rapid development of computing power and data storage technologies and their ability to provide high accuracy prediction, increasing profits and reducing losses. A computerized system can help them decide whether to purchase a property and when is the best time to do so. Every year, housing prices rise, which requires the creation of a mechanism for forecasting future housing prices. Landlords, real estate appraisers, and politicians can use housing price forecast to estimate rent for a house and acceptable sale price. So the study aims to develop a web service architecture capable of forecasting residential rental prices based on apartment characteristics. The proposed machine learning-based web service provides forecasting accuracy and easy integration with modern web platforms. So you can see some service, in this case it's a Zillow service, which can propose for you AI agent to select some house for rent. In practice, machine learning programs, for example, in this portal, support real estate agents and use artificial intelligence algorithms to estimate property prices. However, they are paid and have different monetization models. To collect information about apartment rentals, there should be the standard for describing the characteristics of these apartments to facilitate the collection of data from various sources, such as websites. Depending on the housing market data of individual countries, the effectiveness of methods varies. In some cases, the multiple linear regressions works well, in others decision trees, and in other cases artificial neural networks. Predicted prices don't always match actual rental or sale prices due to the omitted variables or insufficient flexibility of the modeling procedures. This leads to erroneous conclusions in areas that depend on the real estate market. Ordinary least squares or OLS regression is an example of such model, as it allows the contribution of each attribute to the price of an apartment to be obtained by analyzing by regression coefficients. In practice, most big data don't meet the usual assumption of regression and can lead to misleading interpretation. Considering all possible interactions between characteristics can lead to multicollinearity problems in regression and as a result to unreliable standard errors of the estimated coefficients. Then there are too many predictors. In, for example, linear model, its estimates often have high variance, reducing the accuracy of forecast. ARIMA methods can accurately predict housing prices for example, for time series data. The existence of nonlinear dependence of hedonic prices or the utility of housing attributes necessitates the use of non-parametric machine learning methods. Compared to traditional methods, the proposed machine learning-based approach improves, in average, forecasting accuracy in present settings by 25%. Nonlinear analysis showed that all public services, for example, educational institutions, and some private services, for example, entertainment, positively correlate with housing prices within a specific range. However, without understanding the model's logic, it becomes impossible to identify important attributes that affect the price when renting a home or investing in real estate. Neural networks can create nonlinear model without the need to formulate a multidimensional model. However, the disadvantage is the uncertainty of whether the error obtained during the network training will be minimal and the resulting model will not be subject to further training and error correction. As a non-parametric methods, a decision tree-based model, for example, does not require any assumption about data distribution and can capture more complex model than their linear counterparts can. These models can be applied to a combination of numerical and categorical variables without creating massive sets of dummy variables, as typical real estate data contains many categorical variables. Different machine learning methods have different strengths and weaknesses. And if a model performs well on one metric or data set, it does not mean it performs well in all aspects. Hyperparameters in machine learning models are one of the important factors affecting the accuracy of the results. When we choose a machine learning model, we need to understand the final goal: prediction, interpretation of results, or both of them, considering what there is some trade-off between prediction and interpretation. Explainable AI can mitigate this trade-off by preparing the same interpretation as parametric model and providing insights into the causal relations of identified trends. Among the more effective methods of black box interpretation are LIME and SHAPE. For example, LIME means the greater reduction in accuracy than excluding a predictor from the model, the higher importance of the predictor. On this slide, you can see technological scheme of the Auer study. For example, in our first step, it's a gathering data. So we use web scraping to gathering 10,000 data set about housing rent prices in Kyiv. The second one, it's extracting features where we can understand what feature is important and which important impact on price exist. The next one, data cleaning, application of machine learning models, and explanatory analysis, where we try to understand impact of each separate feature on our main result. So it has determined that on average 80% of data companies hold is unstructured and takes the form of images and text. For example, on websites of real estate or rental prices. The volume of these new sources of information is growing 15 times faster than structured data. The inclusion of unstructured data in research improves the performance of predicted models, and the use of advanced machine learning techniques significantly improves accuracy compared to traditional regression. Conducting a rapid and comprehensive property evaluation and real estate market analysis is critical to obtain accurate data for making informed and data-driven decisions to address housing affordable issues. Determining average values for different real estate types is a benchmark for accurate market valuation. This helps prevent over-evaluation and under-evaluation of homes, creating a fair housing market. Automatic determination of housing prices using multiple regression model and machine learning helps support decision-making on renting and selling houses. The application of big data in real estate using computer systems and automated valuation models, or AVMs, supported by artificial intelligence, has the potential to solve these problems. Automatic valuations models and advanced AI will change the appraisal process and assist appraisers in many ways. However, they will not replace the part of the appraisal where the appraiser interprets the data and makes judgments about the impact of the data on value. So, despite machine learning's excellent performance, interpreting the results can be extremely difficult, especially in cases of high model complexity. To address this issue, some researchers have begun using explainable artificial intelligence in housing price studies. For example, shapely values can explain the modeling effects of local interactions that might otherwise go unnoticed. Non-linear relationship between neighborhoods and housing prices can be explored and interpreted using Shapley additive explanations. Shapely values can determine whether each input feature has a positive or negative impact. So here you can see example of such combination of machine learning and explainable AI, where we have a different step from data collection, selection of variables, modeling, and mapping and analyzing it. So here you can see an example of decision tree using geographical coordinates and living spaces to predict rental prices. So the highest level indicates the more important features, and the next level important demonstrates next features using important analysis. So the rental prices model consisted of important housing characteristics, for example, geographic coordinates and variables extracted from images and text, what provides significant in the linear model estimated based on residual mean squared error. PFI, or permutation feature importance, measures the importance of feature in a model by calculating the increase in prediction error after rearranging the features. Important features will increase the model's error. As a rule, the most important parameter for predicting rent are living space, number of bedrooms, and mobility index. So for our research, as was mentioned before, through web scraping, we gathered necessary data from the data source. You can see it here. It's a site Dmytro. Due to limited time for preparation of this data set, we used only most recent information in November, December 2024. Our dataset comprises 1,000 apartment rental listings with 9 characteristics: area, rooms, floor, total number of floors, metro, pencil hour, distance to the center, neighborhood, and price house. In this case, price house, it was dependent variables, and rest of these variables are predictors. So the histogram shows a slight rightward shift, positive skewness, and the median is to the left of the mean. It means what the data is slightly skewed toward higher values of price. For this data set, we prepared pre-processing procedures, cleaning, standardization, and coding of binary characteristics. In the data sets, we selected the dependent variable rental price, and the rest are predictors. The proportions of distribution between training and test samples is traditional 80 per 20%. So here you can see descriptive statistics of this data. So from this slide, you can see average rental price in Kiev in corresponding time period. It's approximately 25,000 hryvnias. So we can see also average square of rented house near 50 square meters, average number of rooms 2, average floor 10, and approximately half of all houses near the metro, and in almost 50% of them pets allowed. You can see also that average distance to center from house approximately 8 kilometers. So, methodology. Our analytical approach addresses 3 machine learning models. It's a multiple linear regression, decision trees, and random forests. In this case, our motivation, linear regression for baseline performance as benchmark, decision trees for interpretable rules, and random forest to robust prediction. We employed standard dividing between dataset, 80 per 20% for training and testing ratio correspondingly. And we introduced model quality criteria, mean absolute error, mean absolute percentage error, and root mean square error. In this case, our model selection prioritizes the optimal balance between predictive accuracy, model simplicity, and real-world deployability. These 3 complementary models provide comprehensive coverage of linear and non-linear patterns. Multiple error metrics ensure robust performance assessment. Results. If we consider decision tree models, then the most influential predictors in the decision model was 3 factors. In this case, it was number of rooms. It's the first one. The second one, it's a area of house. And the last one, it's a distance to center. These factors were frequently used in the 3 branches for data splitting, indicated their critical role in determining rental prices. Our other variables was less important and suggesting a limited contribution to the model's predictive capability. The next one, according to the metrics, linear model achieved the lowest error, while the decision tree exhibited the highest error. Random forest produced intermediate results. We can see that decision tree and random forest have overfitted due to significant gap between train and test error in contrast of linear model. The decision tree performed worse due to overfitting on the training data, as the high tree depth led to memorization of the training examples and poor generalization of unseen data. The random forest performed better than the decision tree due to averaging effect across multiple trees. However, its accuracy was still slightly lower than that of the linear regression model. Thus, it's advisable to try a simple and interpretable model, in this case, such as linear regression, than forecasting rental prices, because our data set has linear relationships. So, comparison of models reveals which features drive property prediction across our 3 models. So we can see in all of these 3 models some set of main predictors. For linear regression, statistically significant predictors were area, number of rooms, and neighborhood. For decision trees, it was also area and number of rooms, but third predictor is different. It's a distance to the center. And for random forest, it's a similar to decision tree, but with a more stable ranking. So in all models, the most informative predictors, the area, number of rooms, and distance to the center. So in this case, due to best performance of linear model, we consider statistical significance of factors. So in this case, we can see what it was area, it was number of rooms, and it was district, in this case, district location in Kyiv. The rest of predictors was insignificant. In this case, because it's a linear regression, we also researched on multicollinearity using variable inflation factors. So in general case, to exclude multicollinearity between variables, VIF have to be less than 10. In our case, you can see that all these variables less than 10. In this case, we see that there is some more than average value 5.4 and 4.8 for area and number of rooms. So it's logically understandable because there are positive correlation between area and number of rooms, but it's have no significant impact on final results. On this slide, you can see our prediction result. In this case, you can see actual price in blue color and predicted price in yellow color. And as you can see, then taking into account this graph, we can see that there are insignificant differences between predicted values and actual prices. So in this case, we can see to assess the reliability of the forecast, we calculated 25% confidence interval, which predicted rental price. Using linear regression, the graph shows a strong correlation between actual and predicted apartment rental prices. On these slides, you can see some proof about reliability of obtained results. We can see from graph above, where you can see dependence between errors and predicted values. So it means that in some cases, we can have overestimation or underestimation of rental price. But in this case, you can see that from 10,000 observation, only few of them significantly gap from average values. So in this case, we can support that we have correct model to predict these results. And on the below graph, you can see dependence between actual value and predicted value. In ideal, we can have a right line, y equals 6. But in this case, we have some small deviation from this line. But in this case, we can see that in average, our predicted results and actual value almost same. Our next step, it's a consideration of our web service architecture. So our developed web service consists of the following main components: front-end, back-end, and storage. Front-end includes form for entering apartment characteristics, for example, area, rooms, floors, etc. The second displays the predicted rental price and compares the prediction with current listings. Back-end, trained linear regression module, processes user internet data and performs predictions, and processes HTTP requests and verifies data. Entity list storage stores lists of apartments and contains historical price data set. On the right side, you can see architecture of this module, where you can see two main sites. It's landlords and people who try to rent this house. And in this case, these models provide some interaction between these two subjects to reveal a price of the house. The next slide demonstrates user interface and functionality. In this service, the user enters the parameters of the apartment and receives a rental price forecast. The user then compares the forecast with the average market price of all apartments with similar characteristics. Apartment filtering in the left side shows the interface, which provides a form where users can input apartment parameters such as area, floor, desired number of rooms, renovation status, district, and others to choose housing price offers. And parameters for forecasting, right side, demonstrates the interface, which provides a form where the users can input apartment parameters to predict housing price. So it's a preliminary output after inputting this parameter with user interface and functionality. Forecast results demonstrates what user receives the predicted rental prices after clicking the forecast button. Additionally, the system displays the price range of similar listings based on the specified parameters. Average price is the actual average price of the apartment with the characteristics requested by the client in the data set. Forecast results is the expected average price of parameter with similar characteristics based on machine learning model. If the actual price of particular apartment with these characteristics is higher than the predicted price, it's necessary to determine the additional factors contributing to this difference. If there are no such additional factors, then the price is inflated. So here you can see discussion and limitations of our research. Each concerns about data quality. So in this case, we can increase accuracy of input data, increasing, for example, a period of time and number of regions. Scalability, where we need a containerization using Docker and a scalable backend. So we can improve our research using sentiment analysis, where we can use also images using text data to improve and increase our accuracy of prediction and risk of overfitting using more complex models, which require hyperparameters to avoid this overfitting. And the main conclusions. I did not repeat it because it was mentioned before. The main problem that for linear structure of our data sets, the linear model have more accurate prediction. For non-linear one, decision tree and random forest will the best choice. Many thanks for your attention. I will be glad to answer.
Thank you. We have short time for questions. Welcome. Rihanna, welcome. Sorry.
If you don't mind. Yeah, thank you so much for your talk. I was wondering, these are quite, so to say, older algorithms, and as far as I'm not an expert in housing prices or anything clear, but as far as I know, the housing price prediction, state of the art is using networks to at least test it or compare it against more advanced approaches.
Thank you very much for your question. The main reason why we don't use more advanced techniques, for example, LSTM or something else, it depends on data structure. Because when we use more advanced methods, we obtain it larger overfitting. And in the case, structure this data more linear, and linear model demonstrate more reliable results using metrics which we demonstrated.
Very useful if you included this in your presentation, like the comparison of overfitting. And I think if you have it, that would be nice.
So in this case, just a second. So,
but you don't have advanced models here. You just have one regression and two tree-based models.
That gap between train and test sets, it's minimal. For example, linear regression. If you can see, for example, decision tree and random forest, the difference is more than 2 times. So in this case, we also was wondering that such simple model demonstrate more reliable results. But for our data sets, it was true.
But my question was about different. So my question was, why don't you use more advanced methods like recurrent neural networks, and have you compared your results with them? Because you claim that recurrent neural networks would suffer from overfitting more, and I don't see any proof in the presentation of that statement. And second of all, they made data, but as you mentioned, you can scrape this data from multiple websites, so the data should not be an issue. And like any overfitting neural networks can be fixed with more data in your case specifically. So I'm still confused about why you haven't chosen to use more advanced technologies.
Thank you so much for your question. So we read this research with first-year PhD students. So it's only our first steps in this case, and he have no possibility to present his result. So it's our first step, and in future we can expand data set and to apply more complicated methods to improve our methodology.
Thank you.
Thank you.
Thank you. Excuse me. Recording is open.
Thank you for very interesting research and very actual research for all internet displaced person maybe, and that's why I have some question. As I can understood, you conducted your research during what time? Yes, 2024. Yeah, and it was only an example on Kyiv.
Yes, it's only example. Only 2 last months of 2024.
Okay, that's nice. And that's why I have a question. Was the factor of security taken into account? For example, availability to shelters. For example, floor of house, because the some floor, for example, 25, 20 floor more dangerous than, for example, first or fourth floor. And how these factors influenced to this result? Because I think sometimes these factors can have greater impact than number of room or distance for center.
Thank you. Thank you for your question. So in this case, our research was limited to information which was uploaded to website of rental housing price. And for example, as separate feature, for example, shelters or something else was absent on this site. So after collecting, gathering all information from this website, we obtained approximately 10 main predictors, which was in all housing prices. And it's a very good idea to increase the number of these predictors to achieve more explainable power of this model. But in this case, we can see that, for example, district or location was more significant. In this case, location, it's a binary variable, and each district in Kyiv was numerated, but some number. And in this case, we can, using this discrete number, to the more the number, the more impact on our rental price. So in this case, if after substitution of this number, our rental price was increased, it means that some combination of characteristics which not included, omitted in this model, was defined by location. For example, in central region, in period of investigation, the price of housing rent was higher.
Okay, just one question.
Thank you for your presentation. The question is the following. Do you take into account the possibility of bifurcations that are connected with bombing of this or the other points in Kiev. For example, Troyeshchina is sufficiently big region, and prices in Troyeshchina are different for different parts. So central regions are sufficiently small. Do you take into account the existence of critical infrastructure in this or the other place, and the bombing of this infrastructure? Thank you.
Many thanks for your question. In this case, as I previously mentioned, one of the important feature which impact on housing price, it was its geographical coordinates. And in different European countries, for example, it's a main attributes. For example, the closer to sea, the higher rent price, and vice versa, as an example. So for Kiev, we, as I said, was limited only all information what was on corresponding Domria website, and in this case, we have no exact impact of shelters or other infrastructure on the choice. So in this case, we was limited only on discrete variable of location, where can help us to understand in which district high price. But in this case, due to average scores which we obtained from our models, we can't expand these results for all districts. So it's a good idea to give more deeper our research, including more important features. Thank you.
Okay. Thank you. No questions. Thank you very much for your presentation, for question and answer.
Thank you. Thank you for you.
And our next presenters. Welcome. The next presentation is building multilingual terminological bridges between language-specific knowledge silos. A lot of authors and presenters is Vadim Ermolayev. Yes. Welcome, Vadim.
This is secret here to that.
This is our next shared class, right?
Yes. No, this is just an error. And well, my feature is also great. So it is very easy to distinguish who will be presenting this research. This work has been done. The work in progress, of course, because we have just started with Dmytro, Chaplynskyi, and the rest of the gang working on this interesting topic. It was done in cooperation with the Technische Informationen Bibliothek of Labels Information Center for Science and Technology and University of Hanover. So therefore, we have the team composed of the representatives of both organizations. So my plan for today is to motivate you to outline our current contributions to show that it's a live work and with progress day by day. I will start with outlining the state of the art and the hidden trends in the state of the art, which opens up some gaps for us for further investigation. I'll outline the approach for terminology extraction, which is 30 years of those multilingual bridges between cultures and whatever, as outlined in the title of this talk. I will show you our early results, which are promising, and share some insights if time allows. For the rest of the details, I will invite you to join me at the lunch, coffee, or whatever break. I have the whole day tomorrow for ad hoc meetings if there is interest. So let's start with the motivation. I thought this is a microphone. Some people have to sleep a little bit more in the nights, but not observe the air alarms in the home city. So I need both. Let's start with the motivation. Well, as we all know, and which is proven by the gathering of people and experts here at this conference, the research is more and more internationalized today, and the tendency is quite clear and stable, which has some highlights and which has the lowlights. So the highlights are, if you have an international team, you have good opportunities to exchange knowledge between domains, across borders, across cultures. So we have people of several nations in the team working on this small project. But there is a consequence, and which is a low light, that such a diversity brings up linguistic and disciplinary boundaries, which have to be overcome in a way. So this is why we're thinking about bridging knowledge gaps between national research communities, trying to soften the barriers, to lowering the barriers, and building bridges. That's a dream, of course. And we do that by developing instruments for for removing lingual barriers, terminological misalignments, so semantic barriers in knowledge acquisition and use, mainly in scientific research contexts. We have a vision of the use of this infrastructure developed by our Leibniz partners, which is an open research knowledge graph infrastructure. And we'll use it as a platform for further development, deployment, and dissemination of the results of this work. So the objectives of this research is to design, implement, and evaluate a novel multilingual and domain-neutral iterative method for automated terminology extraction, also known as recognition. And we target by this objective to fulfill the first task in the workflow for building multilingual scientific knowledge graphs, which facilitates building aligned multilingual thesauri for scholarly domains, like for any scientific discipline you are in and you are lacking this structured knowledge representation. This will lead us to neurosymbolic, as revealed in the previous talk. So the contributions we are highlighting in this presentation is first Extractomat, which is a hybrid iterative domain-neutral ATE, automated term extraction pipeline for English, German, and Ukrainian by the time of submitting this paper for the conference. But now we have already added French and Dutch to make it even more multilingual and to have more possibilities to cross-evaluate it using different datasets. So we'll also share the results of initial evaluation experiments, and hopefully you will judge about the results as similarly to us as promising. Now let us look at the state of the art. What we did, we just traced the evolution of the scientific thought in two related subdisciplines of natural language processing and semantics. The first is
named entity recognition, which is an orange line. And the second is general automated term extraction. And we have built these diagrams based on the numbers of papers in both subdisciplines per year, starting from almost prehistoric times. As you may see here, the number of papers in named entity recognition is about 6 times higher than in general automated terms extraction. And the reason of this, as we assess it, is twofold. First is that named entity recognition is a little bit more practically demanded and appealing. Many people do named entity recognition for very practical purposes in industry. But general automated term extraction still remains a little bit more academic because of, last but not least, the lack of the golden standard data sets, human expert labeled data sets. It is easier to make golden standard data sets for named entity recognition. We have more experts in detecting and recognizing named entities. And it's easier for a human to detect and recognize named entities. For terms, this task is a little bit more complicated and also biased, which I will demonstrate a little bit later in, yeah. So if we look a little bit closer to the general ATE curve, we'll see that there was slight incline to the summit of inflated expectations somewhere in 2022, where the summit has been celebrated by the challenge organized by the colleagues from the Netherlands to compete on automated term extraction based on the actor dataset in 4 different domains and with a golden standard dataset. Of not the best quality, but okay. So what do we have here? We have some inflated expectations rising from 2017 to 2020 here. Here, 2022, we have the summit of inflated expectations, and then we have the slope of the disillusionment if we use the analogy with the Gartner curve. And here we have a slight incline to the, well, hopefully the plateau of productivity. I was modest enough to call it the rise of the neural here. So if we look a little bit more attentively and deeply into the types of solutions, we will see that the solutions started to be developed in around 1970, and the first solution was linguistic. I'm referencing papers, the pioneering papers, which pointed to the solutions. Then some statistical methods came to the podium, and then we opted to start thinking about the interconnections between the concepts. So the graph methods have been introduced, which use the edges in graphs to compute the similarities between the nodes. And then the machine learning methods, the deep learning methods, and finally language model methods have come to the stage and started showing promising and more promising, even more promising results, at least in named entity recognition. So the idea and the takeaway from this slide is that only a hybrid method could give you a chance to push the state of the art. So this is the topology. The methods for automated term recognition are rule-based, which could be linguistic, which could be statistical, which could be hybrid, combining linguistic and statistical parts, could be graph-based, machine learning-based, like classifiers, like hybrid as well, adding linguistic and statistical features to the classifiers, to feature classification. For example, post tags, IDF, semantic information, mutual information, left-right entropy, which led us to embeddings further on in DL-based method, which are also about classifications, embeddings, also hybrid, and finally LM-based, which are doing essentially fine-tuning for a particular domain of discourse, or prompt engineering for few short, using LLM as a judge, and many other approaches. The representatives here, Bert mentioned already, Roberta, Axel M. Roberta, Gline, which is one of the champions for today, I would say, and the line of the GPT stack. So for our solution, I have to confess that we make it hybrid. We use rule-based hybrid as the baseline. We add embeddings which improve rule-based in terms of putting the judgment and ranking into the context of a sentence or several sentence embedding. And we also tried language model based by fine-tuning one of the language models, which I will speak about a little bit later in experimental setting and results. So in general, automated term extraction, the state of the art, well, to the best of our knowledge, there are some papers written by Russian authors, which we do not appreciate to read, mentioning that they started doing the very same thing at about the end of 2024, but for the Russian languages, which is out of relevance for us for today. So the last cross-check point is 2020, this actor competition, and these are the first 5 models and their results on actor. What does it say? It was a multilingual competition. The data set is parallel trilingual, in fact. There are documents for English, French, and Dutch, and this is the performance in terms of the balanced F1 score, and this is the average balanced F1 score. So, and this is the type of the solution. So what do we see here to take away? That the neurals are rising. They are the first, the champions so far. But if we look at really trilingual solutions, we may say that the neurals are not very good in that. I'm not going to dive into details here, but we can do at a coffee break if you wish. So the rule plus extension solution might be sort of more balanced in the current state of the art as presented in the available data and publications. So having said that, we looked also at what has been done in named entity recognition because the approaches are quite similar, though the task itself is a little bit more easy. So these are the results which we have taken from the current state of the leaderboard on CoNLL 203. This is the dataset name. So the results are ranging in time from 2015 to 2023. So also slightly outdated, but anyhow, it's a little bit better than 2022. So the results here are much more inspiring, as you may see. But as you may see as well, this is just on English. In the vast majority of the solutions, only 3 of those declare that they are multilingual, and they're not the champions in terms of F1 score. So the research gaps. In general, automated terms extraction. The first is low performance of the language-neutral, self-supervised, so to say, multilingual rule-based method compared to deep learning-based and transformers or named entity recognition, though this is not a correct comparison, as you may understand. So the difference here is, as you see, quite huge. The next research gap is that we have high overheads for model training or fine-tuning of the neural approaches. So this is not the miracle what we observe in differences in research gap 1. This is just because of the training overhead you have to have. The next research gap we have identified is the absence of the up-to-date general ATE cross-evaluation results. 2020. On actor, the latest multilingual to the best of our knowledge. The fourth is the rarity of multilingual ATE solutions as demonstrated in the previous slides, and the absence of general ATE for Ukrainian, almost non-existing, both in terms of solutions and evaluation datasets. Sorry to say, Marianne. Let's go to the approach. This is a generic ATE pipeline. So we start with texts, PDF, Microsoft Word, any other type of pre-process, convert to plain text, remove the parts which may cause a regular accumulated noise leading to overfitting. Then we extract candidate terms like strings, n-grams mentioned. And then we do scoring and ranking. And here we look at scoring and ranking from two angles. The first is the termhood and the second is unithood. The termhood stands for measuring how strongly a candidate word or phrase, an n-gram, is related to a specific domain. So whether it is a domain-specific term or not. And a unithood measures how strongly words in the multi-word expression link to each other in a stable pattern, belong together. And this is the very, very bird-eye view outline of the solution. What do we have here? We have Extractomet, which is a hybrid proof of concept implementation of a hybrid general ATE method, which includes rule-based, linguistic plus statistical, plus the account for the nested terms in terms of the C-value, or MPCV as a refined method, plus sentence embeddings, which helps us refine the statistical ranking here, which is called re-rank internally, and this is multilingual. Working now for English, German, Ukrainian, French, and Dutch. More details in the paper. I'm sorry, I have no time to present all the technicalities here. I would better show you the evaluations. So we thought about experimental setup in view of the following objectives. The first is we have thought that it would be reasonable to cross-evaluate baseline method implementations which are known from the literature, which demonstrated the best performance before, like for linguistic statistical hybrids, we have C-value basic and combo basic. Like for measures, we do use precision recall and F1, which is a traditional approach here. For thresholding, for cutting off insignificant things, we use the threshold scheme. There are some ways to compute the threshold in different approaches, but this is a little bit out of the scope of this presentation. And the data sets. We have two. We tried it on the two data set. The first is a tiny data set we have developed ourselves, this OTRT. It's a parallel data set in English, German, and Ukrainian. And the technology to build it was very simple. I took my former paper on ontologies of time review and trends, OTRT. This is English. Then we used human experts in time representation and reasoning to refine and review the DeepL translations of this paper in order to ensure that the terminology in the translation is correct for the target language. So, and then we just labeled this text by term, non-term manually. That was the expert way. So it's a golden standard data set, and it's parallel for different languages. The second is Actor, which has been used in 2020 for cross-evaluating the methods for automated terminology extraction. This is the output of our Dutch colleagues. So what is the procedure? We just feed in the data set into the extractor mat. We get the baseline and we look for F1 values precision and recall by the number of the terms included into the above threshold part. And then we add re-rank to improve it and get the improved results. So based on that, this is one more experiment we have run with the objective to check if transformers pre-trained for named entity recognition, which are available, would also work for automated term extraction in general. So we experimented on 3 models: Facebook AI Roberta Large Backbone, Roberta Base, and Answer.ai Modern BERT Large. The measures were the same, precision recall one, and the data set was the English subset of Actor, because all the models have been, so to say, fine-tuned into English. But all 4 domains of Actor. They have domains like corruption, dressage, heart failure, and wind energy. A traditional split for a train test, as you may imagine. So the early results as of April 2025 plus extensions. So this is now the source document colored for manual markup for terms. This is OTRT. Ground truth has been labeled by the author and then rechecked by the human experts who were native speakers in Ukrainian and German. The data set is small, it's just 1 page. Because if you continue with the second, it becomes a little bit too boring. And this is the statistics for OTRT. As you may see here, number of tokens, words here in the documents, it's slightly less than 600. For English, slightly more for German, and slightly less for Ukrainian. If you compare to Actor for all 4 domains, you may see the difference. But this is not the most important difference. I mean, this statistical difference in the number of tokens and number of labeled terms is not that important. The most important thing which differs OTRT and Actor will be revealed later when I show the evaluation results. This is how ExtractMat showed itself on OTRT for all languages. So Not bad, isn't it? Like some named entity recognition models. So it showed us that even using traditional, old-fashioned, whatever you call it, to humiliate us, linguistic statistical methods, if you do inject the proper understanding of the terminology for this particular domain in your part of speech patterns, then you get very good results, which could be further improved by including embeddings or using transformers or whatever. But this is already quite good. Let us now see what happened in terms of for different thresholds. These are the maximal points here. These lines are for languages. We have re-rank, C-value, and basic, and combo basic, the very same result. So what could be taken out from these diagrams? So re-rank and C-value normally provided maximums at higher thresholds, which means that those two methods allowed us to collect more compact term sets with sufficiently good F1 score. Therefore, we have understood that the C-value method and re-rank over C-value is in fact the most effective method among those three baselines that we have implemented. And this is the result on ACTA, which have been done after we have submitted the paper. And when we extended extractomet to French and Dutch to be compared to all the participants. So what do we see here? We just noticed that the results are very different to our previous OT-RT experiment. And a good question is why? And this is why. It is much better on OT-RT because firstly, the post patterns were developed in the view of this OT-RT dataset as a dataset we used to check if it works correctly. And we tried to build the patterns through regular expressions for parts of speeches which could be recognized as terms in a way to somehow mimic the markup of the experts in OT-RT. The second aspect here is that we have much more dense term labeling in OT-RT compared to ACTA. If you just look at the ACTA sets of terms and texts which are publicly available on their GitHub, you'll see that the term appearance in the text is much more sparse than we have here. However, which is also interesting, the shapes of the curves for OT-RT and ACTA on re-rank are very similar if they are normalized by the amplitude of the rank. The second experiment has been run using transformer-based named entity recognition solutions. The idea was to take it as is and find out if it's reasonable to continue working on this way. Would it really work for general ATE or not? So we used the English subset of ACTA, 80-20 split. We trained and named entity recognition model in spaCy using the backbone mentioned here, the Facebook AI, Roberta Large. And we tested on all 4 domains of ACTA and achieved quite good results, as you may see here, for a multilingual solution, which is very comparable to those 3 multilingual candidates which are squared here. So we are somewhere around this state of the art of 2023 at the moment. no miracle, just training overhead. We spent some computation capacity to fine-tune the model, and the result shows itself. You may wish to ask me why that bad? Why didn't we beat the state of the art here? Just because the task is a little bit more complex. We applied it not to named entity recognition, but to automated term extraction, which is a little bit more abstract and more complex. Some insights. Just the outlines. I have some backup slides for those who are interested in details. So the problem was that it was hard to distinguish between the categories of term candidates in terms of their span and in terms of their relevance. Was it an in-domain term? Was it a broader domain term? Was it a common sense term? Was it a non-term? And this is the main difference, by the way, between the OTRT label and actor label, because they were focusing in domain terms. In OTRT, we marked up all the terms without distinguishing in these categories. The idea here, how to solve this, is to use contrastive classification to improve the quality, to find out what of those are in domain, broader domain, out of domain, and probably non-terms. As a side result, we can extract compact document core collections and corresponding core terminologies, as already mentioned implicitly when we discussed the diagrams and the thresholds. The idea here is to use automated generation of silver domain-bounded datasets, which are compact. The third takeaway is based on the statement by which could be extracted from the state-of-the-art analysis that transformer-based models could generalize to languages not seen in training data. And the idea here is to check if cross-lingual generalization works sufficiently well in general ATE, which we have some doubts about. Our grand motive here is to bridge the gaps between the knowledge silos of national research communities, as mentioned in my motivation part. And the idea here is to generate and align multilingual domain-bounded thesauri, which is already possible if you have a reliable ATE solution for several languages, and you can map. You can classify by categories and then map between individuals in the categories. This is it. To conclude, we presented our proof of concept implementation of a 5-lingual domain-neutral hybrid ATE pipeline as a baseline with some improvement using embeddings, which is re-rank. The name is Extractomat, fully publicly available code and data on our GitHub. Promising initial results in experimental evaluation, which I have shown to you. Several ideas on how to improve performance are left for the future work, and several practically important downstream tasks have been also mentioned in terms of going to a higher semantic levels. We're just waiting for some funding for that. Thank you very much. It's a pleasure. And this is the gang. And this is the same QR code.
Okay. Now we have time for questions as alternative of our lunchtime. Okay. Okay, please.
Sorry, Hassan, I know you raised your hand first. It's okay. Okay. So I have a comment on the question. The comment would be about comparison to Connell task for named entity recognition. I understand. I hear the sentiment that ATE is not the same as NER and it's okay, but since you're already using it for comparison, there's another shared task with the leaderboard that is multilingual that you could use for comparison to, and that is the Slav-NER shared task that includes Ukrainian. If you look at Slav-NER from 2021, if my memory doesn't fail me.
It's Slovenian and Ukrainian.
Yeah, it includes Ukrainian.
2 languages.
No, it includes like 6 or 7 languages. Ukrainian is one of them.
Uh-huh.
I'm not sure it includes any of the other languages that you're targeting here, so that's a question mark. But it is a multilingual named entity recognition shared task that has been going on for a couple of years, and it included Ukrainian in 2021. So it may be a good baseline for you to compare the multilingual setting, because from what I saw from your presentation, you have a lot of data on the performance in English of different models and so on.
Yep.
But you don't have anything on the multilingual setting, which is a completely different setting with its own challenges. So I encourage you to look into that research, and maybe it can be helpful for, setting that.
Yeah, no, I just contact them.
And now the question, since the ultimate goal is to create the alignment of terminology, cross-lingual alignment across terminology, have you considered moving not from the text to terms to like further alignment in a graph-based way or whatever way you choose, but maybe starting from the ontologies, like you can take the Wikidata ontology that would be that has already a lot of parallel terminology that you can start with and then expand from there.
Thank you, Marianne, for the question. Well, in fact, we're going both ends. Dmytro is now working with Wikipedia to do this stuff for machine learning as a domain, and perhaps he'll have some results to share in the near future. And as for the ontologies, I would not say that it could be a right way to start with an ontology, because this is the way to build ontologies.
Yes, but the currently like tags are also used to expand the already existing ontology. So you can have an ontology with terminology that is already there because there are already available ontologies for that.
Yes.
You can find them in the text, and then it can help you find more terms that you can then inject in the ontology.
I'd rather say that ontologies could be used to, so to say, high-level ontologies. The common sense ontologies, like BFO, like UFO, like many others, we both know, could be used to provide hints and mapping through the subsumption hierarchies, at least for English, and then you may easily map it to a different language, which is already done for some of those ontologies with an aim to make them multilingual. This could be a way for verifying the correctness of the result. This could be a way to simplifying the stuff. And yes, we are looking in this direction.
Okay, thank you so much. Can I ask like the last one, very tiny one, since we have Vadim here and they have a question for Vadim that he likes to ask other presenters. How do you define term in your study?
I will give a very, very short answer. In my last tutorial at the PhD Summer School on Research Frontiers, I have several slides on that, so I can share the presentation.
Okay.
Yeah, thank you very much. Really interesting topic. I was wondering, based on the assumption that multiple domains might be more challenging to distinguish between, especially if they say use the same terminology with different meanings in the same language, in contrast to differentiating the terms between different languages. What would you prioritize? Training models on one language that differentiate domain terminology from each other, and then using training multilingual models that can still differentiate domains? I was wondering if one can prioritize, or if it makes any sense to prioritize the domain term recognition within one language, and then using an agentic system approach to align the different languages. So one would have multilingual system instead of one multilingual model.
Thank you for a question. Great. A great question. We're thinking about that for quite some time already. So, and came up with a conceptual idea of an iterative solution for that. So we start with a baseline for a domain and a language. We collect the representative set of documents within the domain, and we do this natural language-based terminology extraction for this domain. After that, we extract or retain the list of the most significant terms, which is saturated. And then we use this list of significant terms, the core term set, extracted at the first iteration, to make links to the source documents and use the source documents as a data set to fine-tune the language model, which will be informed about what to extract from the text within this domain. Iterate even more until it's saturated to a stable high-impact term set. That is the way we're pursuing to go. This could be repeated for languages, and then we have to build a knowledge graph here and a knowledge graph for a different language based on a common higher-level ontology as a namespace, for instance, and then we do mapping, including the possibility to make semantic and structural mapping between the branches in this multilingual knowledge graphs. This is the way to go, in our opinion.
Okay. Thank you very much.
Thank you.
And let's thank our presenters and for very interesting presentation, and thank you all participants for discussion and very interesting talk. Thank you.